All right, today we're going to talk about the chain rule. It's really, really hard for me to overstate exactly how important the chain rule is. I have Calc 2 students who a lot of times mess up on a problem because they forget to use the chain rule when taking a derivative. It's also really important to understand when you need to use the chain rule. And what we're going to be doing is using the chain rule to find derivatives of composite functions. Now, we talked about composite functions in the previous chapter. We talked about writing composite functions. We talked about evaluating composite functions. It's really important that we recognize when we have one, because that's the biggest thing I hear from students is like, well, I didn't know that I needed to use the chain rule. So understanding when we actually need to use it is key. But that's what we're going to focus on today, applying the chain rule to find derivatives of composite functions. Slopes of tangent lines, just like I said, we're going to be doing that in every single section, and equations of tangents, and then we're going to continue to apply derivatives to applications. So if you will notice that the last page in your notes here is blank. It's page 8, I think. Why are my pages numbered different? I don't know. Chain rule, I don't know. Oh, well. Oh, no, it's not 8. I'm looking at the last section. I was going to say, I thought that we could write a couple of different examples of what composite functions were and weren't on page 12. So it's at the end of this section. There's a blank page. So I'm going 9, 10, 11, and then 12 is blank. So on page 12, I'm just going to give you some examples of what composite functions would be, and then we can compare them to their non-composite counterparts. Okay, so this is on page 12 of your notes. It's a blank page. And we're going to talk about what is and what is not a composite function. Okay, so we're going to make a column for not composite. And we'll make a column for composite. So a classic example of something that would be not composite would be something like y equals x squared. Remember that when we're talking about composite functions, we usually are thinking about these in terms of an inside and an outside function. Well, here, the inside function would just be x, and then the outside function is just squaring x, but there's not a function of x in here. It's just x. The difference would be for the composite function, something like, let's say x plus 1 squared. Now it's composite, because now you can see that the inside function is no longer just x, it's a function of x. It's x plus 1. So that's something that you'll see here, taking derivatives of composite functions. Now, this is something that we're going to learn how to do today using things like the chain rule. Previously, when you saw a composite function like this, where it was just a binomial squared, you went through the process of taking x plus 1 times x plus 1 and rewriting it, and then you took the derivative. So you're going to have some options here for some of these problems. Now, something where you're not going to have an option would be a composite version of a square root function, for instance, or maybe a cube root or a fourth root, any of these radical functions. Y equals the square root of x is not a composite function. It's just the inside function is just x. But we could switch that up to be a composite function if we just called it like y equals the square root of, I don't know, 3x squared plus 1. Okay, so now you're no longer just taking the square root of x, you're taking the square root of a function of x, where the inside function is just another function of x. So you'd say the inside would be f of x equals 3x squared plus 1. The inside of this function would be x plus 1. The inside of the new one is 3x squared plus 1. See what I'm saying? So for something like this, if we were going to try to take the derivative of this function, you don't currently have a way to rewrite this so that you can get it to match the derivative rules that we already have. So a square function, a square root function, those are big ones. We're going to run into other composite functions down the road, especially when we get into chapter 5 and we start adding in some of those transcendental functions. But here, these are mostly the things you're going to see. You might not always see radical notation. You might see something like x to the, I don't know, like 1/5 power, for instance. This would be not composite Whereas if I wanted to switch that up, I could say that it's y equals 2x plus 3 to the 1/5 power. So this function would be a composite function, whereas that one is not. This is just x. And then on the right-hand side, we have a function that's not just x, it's 2x plus 3. So that would be composite. So composite functions will need the chain rule in their current forms, unless you can find a way to rewrite them. And sometimes you will be able to. Like with the first example, you could rewrite this and use your regular derivative rules. But with the next two, you don't have a way to rewrite these using your current derivative rules. That being said, let me remind you, and I know I get very upset about this stuff, but I just want to remind you that y equals 2x plus 3 to the 1/5 power does not equal 2x to the 1/5 plus 3 to the 1/5. You cannot distribute the exponent. Okay, so you cannot do this. This is a no. Okay, so if you're thinking like, well, why don't I just rewrite this and then I can use the basic differentiation rules from 3.1, you can't do that. You can't. Same thing, I could say that, same thing for this. This is not equal to the square root of 3x squared plus the square root of 1. You cannot split up a radical using terms, using addition and subtraction. You can only split up a radical into separate radicals using multiplication and division. So this is not going to fly. You can't rewrite it. So if you're thinking like, oh, I'll just make my life easy, square root of 3 times x plus 1, no big deal, back to 3.1. You cannot do that here. These are just rules from algebra. They get misused all the time. So I'm just reminding you of them so that you will not make these mistakes. I had some Calc 2 students who nicknamed these the terrible awful, because these were the terrible awful things that students would do that constantly led them astray. And this is coming from a Calc 2 student. So this is stuff that students are constantly getting wrong with their algebra rules. So don't think it's just you. So if I say the terrible awful, this is what I mean. Don't do these things. Don't do that. Okay. All right. So these are composite functions. This is mostly the type of thing you're going to be seeing today and in this section. Oh, you know what? I did want to show you one more thing because it sort of relates to an example that I'm going to be doing with you in a couple minutes. An example of a function that would be not composite would be y equals 1 over x. But if we wanted to change that function, because remember, I could always rewrite this as x to the negative first. An example of a function that would be composite would be something like 1 over 3x plus 5. So I know this doesn't really look composite because you're not seeing like that there are parentheses and an inside function. But if you were to rewrite this function on the right to be in the same form as the one on the left, you could move this expression up into the numerator. So you'd have to write it as the quantity 3x plus 5 to the negative first power because the whole thing's in the denominator and the whole thing's moving up. So the whole thing had an exponent of 1 on it. If you want to think about it like that, it was 3x plus 5 to the first, that whole quantity in the denominator. When it comes up, it gets taken to the negative first. So we're going to use this idea here in a couple minutes, but this is a composite function. Notice the inside function is not just x, it's 3x plus 5. The function on the left is not composite. So this uses rules from 3.1. You cannot do that here. You can't distribute the exponent to rewrite it. So you're going to have to, you could use the quotient rule, but we're going to talk about how to do this today using the chain rule. And I'm going to kind of show you the difference, and then you can decide down the road, do I want to use chain rule or do I want to use quotient rule when I see something like this? Usually I have a general rule that I follow there. All right, so that's an example of what composite functions look like. Now we're going to talk about the chain rule finally. Okay, so the chain rule is you are going to take the derivative of g, just acting as though there was no inside function f of x that was something other than x. So you're going to take g prime of f of x. And you're going to multiply it by the derivative of the inside function, which is f prime of x. I find that students will do this wrong because they will take the derivative and put it inside g prime. Make sure that we're going to take g prime, just ignoring the composite function for just a minute, and then we're going to chain it on at the end. When I say chain it on, I mean multiply by the derivative of the inside function. Now, specifically for powers, we have this general power rule that states that if we're taking the derivative with respect to x of some function f of x to the nth power, well, just like we did in 3.1, we can sort of use the power rule. We just need to account for the fact that we don't just have x to the n, we have a function of x to the n. You can bring the exponent down, rewrite the inside function, decrease the power by 1, and then you can multiply by the derivative of the inside function. So it starts out basically doing the exact same thing as what we've been doing with our derivative rules from 3.1. The only difference is that if this inside function is composite, we have to multiply by its derivative. All right, let's just go ahead and get started. I'll show you how this works. Find the derivative. I'm going to put 2 examples on this page. The first one is y equals the cubed root of 3x squared minus 5x plus 1. Okay. Now, just like we did in 3.1, it's going to be much easier for us to evaluate this derivative if we rewrite this radical notation using a rational exponent. So I would not leave the cube root as is. You're going to want to rewrite this as 3x squared minus 5x plus 1 to the 1/3 power. So that would be the first step. So start out just like you would have in 3.1, doing that first step of rewriting the radical. Now that we've rewritten y, you can go ahead and use this general power rule on it. You have some function of x to the nth power. The power in this case is 1/3. But when we take the derivative, we have to also remember to chain on the derivative of the inside function. So we're just going to ignore the fact that we have a composite function for just a minute. I'm going to bring the 1/3 down. So the 1/3 comes out front just like it would have in 3.1. We're going to rewrite the inside function as it is. Don't take its derivative yet. Just rewrite it. This is where I see everybody go wrong. They're like, I don't know what to do with this inside. Ignore that it's composite for a minute and just rewrite it. Decrease the exponent by 1. So 1/3 minus 1 is negative 2/3. Now, the new material comes when we multiply this by the derivative of the inside function. So if you're thinking about it in terms of this formula, this would be your inside function f of x, and we need to multiply by its derivative. So just what's inside, in this case, parentheses, you won't always see parentheses, but we're going to multiply by the derivative of the inside function. So if you want to think about it as f of x, that's fine. Call it f of x. I don't want you to get confused because I know this is y, but I'm just sort of going back to this formula up here. The derivative of the inside function is 6x minus 5. Don't forget to use parentheses. That's another big thing that gets missed. This whole thing is getting multiplied by this whole thing. This right here, the 6x minus 5, is f prime of x. Now, this is the derivative using the chain rule. I am going to simplify this a little bit. There's not a whole lot you can do here, but I'll at least write this as a fraction and make this exponent positive. And then I'm just going to leave this 6x minus 5 in the numerator. So to simplify your derivative, we'll have 6x minus 5 in the numerator. In the denominator, this 3 from the denominator is going to stay in the denominator. And then this negative 2/3 exponent, I'll just make positive 2/3. And this is the derivative of our function in example 1. Usually I have students at least multiply this 1/3 into the parentheses. If I don't specify to make the exponent positive, then you can leave this negative 2/3 expression alone. But I don't know, this just seems not so simple to me. So I like to have it a little more concise. Let's do another one. So this is going to be y equals 3 divided by x squared minus 1. Now, you actually have two different ways of doing this. You can use the chain rule or you can use the quotient rule. I'm going to show you both, and you'll see that your answer might look a little bit different depending on which method you use. Now, students usually see something like this, and they're just like, okay, obviously it's a quotient. I'm going to use the quotient rule. You can always use the quotient rule when you have a quotient as your function. Anytime you have a rational function, feel free to use the quotient rule. But I'm going to show you an alternative. If you like it, great. If you don't, fine. I'll show you the quotient rule first. We'll call that method 1, quotient rule. And this was from section 3.2. Remember that we had f prime g minus f g prime all over g squared. So I'm going to call the numerator f and the denominator g. And then for the quotient rule, I have f prime g minus f g prime all over g squared as the derivative. Okay, so we'll go ahead and find that. Should stick. I'm like obsessed with Flair pens now. I got this new pack at Target today. Obsessed. I can't stop buying them. It's all these guided notes. All right, let's go ahead. Y prime is f prime. Now, f is a constant, so f prime is 0. So f prime g, I mean, you can rewrite the g, but it's just going to 0 out. Minus f times g prime. The derivative of g is 2x. All divided by g squared. Now, when you simplify this, the first term zeroes out, and then you just end up with negative 6x divided by x squared minus 1 quantity squared. This is fine. If you like it, stick with it. There's no reason to change if you like to use the quotient rule. The reason I say to maybe change it up and use the chain rule is because in this case, you end up with a numerator that's a constant and its derivative is 0. So it's a little bit tedious, I guess, to include this step. So my suggestion is whenever you have a numerator of your quotient that's constant, you might want to use the chain rule. You don't have to, but it would maybe be easier in this case. So method 2 will be chain rule. Now, if I had a numerator that was 3x instead of 3, I probably wouldn't use the chain rule because then I'd be doing chain rule with product rule, and that would complicate things a little bit. But in this particular instance, I can use the chain rule because I have a constant function. I'm going to rewrite it as 3 times x squared minus 1 to the negative first. So we're taking that entire denominator and moving it up into the numerator with the exponent of negative 1. So remember, this was your original function, and you could always think about this as being to the first power in the denominator, and then when you move it up, it becomes the negative first power. So now I'm going to go ahead and take the derivative using the chain rule. Now I'm hoping, I know it's sort of hard to see these hypotheticals, Maybe I'll add an example on that extra sheet we have. But if this was 3x instead of 3, you'd have a 3x out front, and then you'd have two different factors of x, factors for functions of x getting multiplied. So maybe we'll add that example next, just so you can see the difference. I don't like to only speak in hypotheticals. Let's go ahead and take the derivative. I'm going to keep the 3 right where it is. I'm going to bring down the exponent. I'm going to rewrite the inside function, just ignoring it for just a minute. Decrease the power by 1. And then I'm going to chain on or multiply by the derivative of the inside function. So your inside function in this case is x squared minus 1. Inside function. I don't want to call it f of x because I already relabeled f of x to use the quotient rule up there. And now it's going to look confusing. And then this is the derivative of the inside function. So I'll say derivative with respect to x of the inside. Now we'll simplify that. So you can see that there's a little bit more work to do with simplifying this, but you can get it to look exactly the same as the derivative looked when you use the quotient rule. So I have a -3 times 2x, which is -6x. And then I can move this x squared minus 1 to the -2nd into the denominator with an exponent of +2. And you get the same thing. Okay, I'm going to go back to that page 12 where I was illustrating composite versus not composite. So I can just sort of add a note here to just explain the difference if we had 3x instead of 3. Right? I don't have an example like that prepared, do I? I don't think so. I don't want to be repeating this twice. It all gets so jumbled up. I'm going to do that real quick just so that you can see the difference. Because that's another thing. Students are like, how would I have known to use the product rule? And I just really want to make sure that's set for you so you know when you're supposed to do what. From example 2, if we had, for instance, y equals 3x over x squared minus 1, well, of course, that's going to change your derivative. And this we did something similar to in the last section for using the quotient rule. So I don't want to do the quotient rule over with it again. But if you wanted to do the chain rule on something like this, just notice how it's different very subtly between having a constant 3 and then a variable 3x. So it's a little bit of a change that makes a big difference in our solution process. So if we decided to do that with the chain rule, remember with the chain rule, what we decided to do here was we rewrote the function as a product and we moved the denominator up to the numerator with a negative exponent. We could do that here. But now this needs the product rule. The reason is I no longer just have some number multiplied by a function of x to a power. I have some function of x that's being multiplied by another function of x to a power. We need the product rule anytime we're multiplying different functions of x together. So notice here, we don't need the product rule. Here we do. I know you might be like, why is she harping on this? It's because I've been teaching calculus for a lot of years and I constantly have students unsure of when they're supposed to do what. And I really want to make sure that this is clear, that we understand when each rule is needed. I mean, it's one thing to know how to apply the rule, but if you don't know when you need to use it, then it's not going to be that helpful to you. All right, so let's do this with the product rule. We would relabel these functions to be f and g. I cannot get over this pen selection I have. It's crazy. Okay, so this will be f. That whole thing will be g for the product rule. And remember, the product rule says that y prime is f prime g plus f g prime. Okay, so we're going to do that now. Y prime is f prime, so the derivative of 3x, which is 3, times g. I'm going to take the whole function g, which is x squared minus 1 to the negative first, and then plus f, which is 3x. And now I need G prime. In order to get G prime actually needs the chain rule. So if I'm just looking at G here and I need to multiply by its derivative for the product rule, I'm going to bring this -1 down, rewrite the inside function, decrease the exponent by 1, and then I have to chain on the derivative of the inside function. The derivative of the inside function would be 2x. So this would be f prime g f. This whole thing is g prime. See the difference? Okay, so it's bring down the -1, rewrite the inside, decrease the power by 1, multiply by the derivative of the inside function. So this becomes a little bit harder when you decide that you're going to take a quotient and use the product rule with it. Because now not only are you using the product rule, but you're using the product rule and the chain rule. So if you have a variable in the numerator and a variable in the denominator, I would suggest just using the quotient rule. You will also get it to simplify much more nicely, because in this case, you've got a little bit of work to do to make this look nice. I don't know if I want to spend a lot of time talking about it, but I mean, you would end up with two different terms that you'd have to combine. Whereas if you were using the quotient rule, this would all just pop out as one fraction for you. So you'd have minus and then 6x squared over x squared minus 1 quantity squared. And then you'd have to combine those together to get it to match what you'd get with the quotient rule. And knowing where this is heading in chapter 4, it's a lot easier if you have your derivative written as one fraction. So this is something that you can do, but in general, my guidance would be, if you're looking at a function that's a quotient, use the quotient rule unless the numerator is constant. Okay. I know I just said a lot there, but you know, the nice thing is it's on a video, so you can always go back and rewind and be like, wait, what did she say? Because I'm sure that you're all rewinding and wanting to listen to it all over again, right? Okay, so that was the first two examples of using the chain rule. You're going to see sometimes some examples that have a little bit more going on with them. Yeah, more than that. So let's do some more. Cannot get over these felt tip pens. Example 3. You know, I'm not sure if they're bright enough, but we might have to switch. Maybe this color should be more for highlighting things. Okay, no. H of x equals, well, let's just call it y. Y equals x plus 2 quantity cubed times 2x minus 1 to the 5th. Now, we need to find y prime. We're going to have to do that using the product rule and the chain rule. So notice again, we have a product of two functions here. So this needs the product rule. I wonder what this color looks like. Needs product rule. We are multiplying two different functions of x together. So definitely need the product rule. Now let's go ahead and label them, because each one of these products will have a derivative that needs, each one of these factors will have a derivative that needs the chain rule, I should say. So I'm going to label them. Let's see, this one can be f. And then the other one will be g, since we talk about our product rule in terms of factors f and g. So let's find f prime now, since we know we're going to need that for the product rule. Maybe I should remind you of what the product rule is. I know we just talked about it on the previous page. Y prime is f prime g plus f g prime. So we need all of these components. We have f and g, we need f prime and g prime. So f prime of x We're going to bring the exponent out front, ignore the composite function for a sec, decrease the exponent by 1, and multiply by the derivative of the inside function. Now, in this case, the derivative of the inside function just so happens to be 1 because the inside function is just some linear function where your lead coefficient is 1. So that's fine. If you want to just rewrite it as f prime is 3 times x plus 2 squared, you certainly don't need the 1. That's fine. And then we'll take g prime, again, using the chain rule. So g prime of x, we're going to bring down the exponent, rewrite the inside function, ignoring the composite function for a minute, decrease the exponent by 1, and multiply by the derivative of the inside function. Now, I'm going to go ahead and multiply between the 5 and the 2 right now, just to get these two simplified a little bit more before I start putting everything together. I also want to note, make sure, I know sometimes we see parentheses and we automatically just start distributing. You cannot distribute the 5 into the 2x minus 1. So if you see the parentheses and you want to say, oh, it's 10x minus 5 to the 4th power, don't do that. You can't take this 5 and distribute it into a 4th power because the 5 doesn't have a 4th power on it. So it doesn't work that way. So just be careful. I know it's automatic for us. We see the parentheses we want to distribute. Stop yourself. Don't do it. All right, we're going to put this together using the product rule. So we have y prime equals f prime g. So 3 times x plus 2 squared, that's f prime. And then g is 2x minus 1 to the 5th. Plus, and then we'll take f g prime. So right now I have f prime g. F prime g plus f g prime is 10 times 2x minus 1 to the 4th power. So there's your f, and here's your g prime. Now, we're going to try to simplify this a little bit. There's not a ton you can do, but notice how you've got two separate terms here. I know there's a lot going on, and sometimes it's hard to see because there's just so much going on. If I were to look at each term on its own, remember terms are values we add and subtract. We're taking this whole thing and adding it to that whole thing. One thing I can do to simplify is to factor out the GCF. Each one of these terms, if I were to think about it like this and like this, has a common factor of x plus 2. Now, I can only take out as much as they have in common, but they each have x plus 2 squared in common. That one's got an extra one that we'll just leave. So I can take out this x plus 2 squared, and I can also take out a 2x plus 1. I have it to the 5th power, and I have it to the 4th power. I can only take out the least number of things that I see, which is to the 4th power. So I'll take out 2x minus 1 to the 4th. Now, I factored that out, and I'm going to write what's left over. When I factored it out, I still had a 3. Both of those now, the 2 factors are gone. Well, they're outside. They're not gone. And then I took out 2x minus 1 to the 4th, but this one had a 5th power on it. So I have one more left over inside the parentheses. Just the 1st power. So 5, take away the 4, gives me 1 left over. And now I have plus, let's see, I have this 10, which I'm going to write in front just because we usually leave our constants in front. And then I have x plus 2 that I took out. I took out 2 of them. That still leaves me with 1 factor of x plus 2. And then I took out all of the 2x minus 1s. So this is almost done. I just want to do a little bit more simplifying inside the parentheses. But notice already how this is going to look so much nicer. Maybe you don't think so, but I think so. X plus 2 squared times 2x minus 1 to the 4th times. And this is going to become 6x minus 3 when I distribute, plus 10x plus 20. And then one more time, I'm going to simplify inside these parentheses so we can get this looking tip top. So I have 6x plus 10x is 16x, and then plus 17. That's negative plus 20. And now I have my derivative. It is lovely and beautiful, and it can't be further simplified. And it looks way better than this. I don't even know if WebAssign will accept this, but this one's really nice. It's just completely factored. Lovely. It's lovely. But that's your product rule and chain rule. So the interesting thing about stuff like this, though, is I think sometimes the calculus is easier than just the algebra. Sometimes students are like, yeah, I got the derivative. I just can't simplify it. So if you're in that boat, you are not alone. Please go to the tutoring center. It's free at ECC. They're open tons of hours. Anybody can help you simplify your algebra in there. And pretty much anybody should be able to help you with derivatives. Maybe not every single person, but they should always have a tutor in there who can help you with calculus. Please go in there if you're struggling with algebra. I don't want that to be the reason you fail this class. Not that you will, but if it were to happen, I would hate for it to be because your algebra skills were not where they should be. All right, we got one more on this page. Let's see, example 4. This will be y equals the square root. I'm making a big square root because it's going to have a quotient under it. In the numerator, 3x plus 1. In the denominator, 2x plus 1. This is going to be one of those problems where the simplifying is harder than the derivative itself. Now, I'm going to remind you, when we saw radicals in any of these previous sections for derivatives, we mostly probably just saw them in 3.1. We always rewrote them so that we had a rational exponent. So I'm going to do that first. So instead of writing this as just one whole square root, we can write this as 3x plus 1 over 2x plus 1 to the 1/2 power. Now, there are a couple things you can do here. Because you have a quotient to a power, officially you could take each piece, the numerator and the denominator, to that power. I'm going to leave it though, and we're going to just use that general power rule with this function. I'm going to bring the exponent down, rewrite the inside function, decrease the exponent by 1, and then the hard part will just be multiplying by the derivative of the inside function. Now, since we know we're going to have to do that, you might want to go ahead and label your inside function something like f of x maybe. I'm going to do that. So our inside function is just going to be this rational expression, 3x plus 1 over 2x plus 1. And I'm just going to go ahead right now and go through this step of finding its derivative. So let's call it f of x. And now to find f prime of x, we're going to need to use the quotient rule. And then we're going to go back and use the full chain rule. All right, so I think I said that audibly in one order, and then as I was saying it, I was like, let's start the chain rule and then do this. So it does not matter the order in which you do these particular steps. I'm trying to figure out what order would make most sense to you. So let's go ahead and take this derivative using the chain rule, maybe like you normally would. And then when you notice we need the derivative, we'll find it. Maybe we'll do it that way. Okay, so y prime is, I'm going to bring the 1/2 out front. I'm going to rewrite the inside function. And I'm going to decrease the power by 1. I kid you not, I've had students who have left their derivatives just like this, and they're like, all right, I'm good, I'm done. No, you're not done, because you have to chain on the derivative of the inside function. So in order to do that, we need to find the derivative of the inside function. So let's do that. I'm just going to note this times d dx of the inside function. And then we'll find what that derivative is. Okay. So let's go ahead and find this using the quotient rule. There's really not another way that I would do this derivative. So if f of x, we've already stated f of x will be the inside function. Oh gosh, I called it f of x, didn't I? And I'm going to be using the quotient rule, aren't I? Oh, she's having regrets. I wanted to call it h of x because you know that when I use the quotient rule, I like to label the pieces f and g. All right, I'm gonna just call this h. H of x. You know, the only thing about the felt tip pens is that they don't work very well with the whiteout pen. So I'm going to have to, it's okay, just h of x. There we go. When I write slower, it's better. Okay, so the inside function will be h of x. So if the inside function's h of x equals 3x plus 1 over 2x plus 1, remember that when we use the quotient rule, we always label our derivatives or our components, f and g. So we'll say f of x is 3x plus 1. G of x is 2x plus 1. That means f prime of x is 3. G prime of x is 2. I hope you're getting really fast at taking these really basic derivatives. Okay, let's go ahead and use the quotient rule now. Remember to use the quotient rule. We're taking f prime g minus f g prime all over g squared. H prime of x is f prime g minus f g prime divided by g squared. Notice how I put parentheses around the 3x plus 1. I even put parentheses around the 2. When I drop stuff into the quotient rule, I want to make sure that this minus sign gets distributed wherever it needs to go. If you don't put parentheses around it, then you'll just think this is minus 3x plus 1, I don't know what, times plus 1 times 2. And then it'll just be minus 3x plus 2. Don't do that. Let's be accurate here. All right, so we'll have 6x plus 3 minus, and then I'm going to go ahead and just sort of distribute two things at the same time. So this will be 6x and then minus 2. It would be plus 2, but it's got this minus sign that's being distributed. 2x plus 1 quantity squared, and you end up with the 6x's are additive inverses. They're gone. 1 over 2x plus 1 quantity squared. Okay. I'm having some regrets because I should have spaced this out a little better. We have a lot of simplifying to do. But now I can bring this back. And I know that y prime is 1/2 times 3x plus 1 over 2x plus 1 to the negative half multiplied by the derivative of the inside function, which we just found was 1 over 2x plus 1 quantity squared. Now, officially, this is the derivative of our function, but it doesn't look so great. It needs to be simplified. And if you're kind of wondering, well, like, what could I possibly do to simplify this function? I'm going to tell you one thing that maybe will be driving you crazy is that you're noticing that you have 2x plus 1s in both of these denominators. And you're like, okay, I feel like I should sort of combine these. Well, you should. We're going to simplify this next. So I'm going to bring our derivative down and we're going to simplify it. Actually, there's not a whole ton to do, but we do need to simplify it. I'm going to leave this 1/2 right where it is in the front. Now, when you have a negative 1/2 power, it's kind of like how if you have a negative exponent, you can switch the position of the fraction. when you have a numerator and a denominator, you can swap them and then you can make the exponent positive. So that's what I'm going to do to make this a positive exponent. And if you're wondering why I would do that, well, you are going to see how this is going to allow us to simplify our derivative. All right, switch the numerator and denominator and make the exponent positive. That is a rule from algebra. I want to say the rule is I'm writing and you can't see it. Algebra. It's like a over b to the negative m is b over a to the positive m. Something like that. But this is a rule that we're using here to simplify. Okay, now there's another thing I can do. I can go ahead and split up this quotient because I'm dividing. If I was adding or subtracting, I can't split it up. But because I'm dividing, I can split this up. And the reason I want to is because I want to be able to combine these 2x plus 1s together into a simplified expression. So I can rewrite this, and this is all going to seem like it's happening so fast. 2x plus 1 to the 1/2 power divided by 3x plus 1 to the 1/2 power. See, nothing has really changed except we've used this exponent rule from algebra. And then I'm going to put this 2x plus 1 squared, keep it in the denominator right where it is. The algebra rule that I am using right now is, what am I using? A over b to the n is a to the n over b to the n. So that is the exponent rule that we're using. See how if we know our rules from algebra, it makes calculus so much easier. And if we don't know our algebra, it makes calculus seem so much harder. I mean, we already found the derivative. We're just simplifying. Okay. So I can take the quotient to a power as the power of powers on the quotient. And now I can go ahead and simplify using another algebra rule. I know we've talked about this one before, but if I'm taking the same quantity and I'm dividing, I can just subtract the exponents. Let's see, if I'm dividing, I always have a way I say this. Let me see. If I'm multiplying with the same base, I add the exponents. If I'm dividing with the same base, I subtract the exponents. So let me figure out where to put this algebra rule. Algebra. If I'm dividing with the same base, I subtract the exponents. So I would say this is a to the m over a to the n is a to the m minus n. We talked about this in the last chapter. That's what I'm going to use here to simplify the 2x plus 1 to the half divided by 2x plus 1 squared. So I'm just going to take my derivative. 1/2 still stays. The 3x plus 1 to the half is going to stay in the denominator. There's nothing I can do with that. But with the 2x plus 1, if I take m minus n, I'm taking 1/2 minus 2, and that leaves me with negative 3/2. So 1/2 minus 4/2 is negative 3/2. So that quantity is going to stay in the denominator, but with a power of 3/2. So this is going to be the square root. If you want to write it as a radical, fine. If you don't, leave it as a 1/2 of 3x plus 1. And then in the denominator now, I'll have 2x plus 1 to the 3/2 power. This is your simplified derivative. I know, it seems so crazy, but it's not crazy. It just took a little bit of work to get there. Okay, it wasn't even a lot of work. It's just a couple of algebra rules. Okay, we're going to use this again. On the next page, we're going to talk about finding an equation of the tangent line to the curve. So we're going to bring this back in a second. We don't have too much left to do here, but we do need to talk about find an equation of the tangent line to the curve. I'm going to give you the same curve we just went through in the last example because we already found its derivative. And the curve is y equals the square root of 3x plus 1 over 2x plus 1, all under the radical, at the point 0, 1. So it's very important I give you that point. In order to find an equation for the tangent line, I need a point and a slope. We have a point. We just need a slope. In order to get the slope, I'm going to use the derivative. The derivative gives me a general formula for finding the slope at any point that you are given. So I'm going to pull back our derivative. Recall, I know it was only like a minute and a half ago, that y prime was 1 over 2 times the square root of 3x plus 1 times 2x plus 1 to the 3/2 power. And that was just from the previous example. So nothing new there. We already found the derivative. Now we'll use it to find the equation of the tangent line at 0, 1. Okay. I need a point and a slope. I have a derivative. Now I'm going to evaluate y prime at 0 to find the derivative at 0. So to do that, I'm going to take twice the square root of 3 times 0 plus 1 times 2 times 0 plus 1 to the 3/2 power is 1 over twice the square root of 1, and then 1 to the 3/2, which is still just 1. So your slope is a half. In order to write the equation for the tangent line, you just need a point and a slope. So for my tangent line, I'm going to use y minus y sub 1 is m times x minus x sub 1. And you get y equals 1/2 x plus 1. You can check this in your calculator if you'd like. I'm not going to put this one into my calculator, but feel free if you'd like to check that. Or if you just think it's really cool to see, which it is. Sometimes you got to just do that to get a little boost, a little mood boost. See some cool stuff. All right, but you don't want me to do that. You want me to finish the last example. So that's what I'm going to do. Let n of x equal, I'm going to give you a function, the cubed root of 60 plus 2x quantity squared. Notice how I keep rewriting my radicals to be longer if I need them to be longer. I did that here too because I stopped it and I rewrote it. It's really important that we make sure that our radicals include everything they're supposed to, because sometimes you end up with a lot of steps in a problem and you end up shortening your radicals and then you think things aren't in the radical when they are. So just be careful about that so that you can make sure that you're actually writing what you intend to write. All right, so here's your function, n of x. It gives the number of viewers of a particular television show in millions in its xth week. Find both the number of viewers in week 2 as well as the rate of increase in viewership in week 2. Rate of increase? It's talking about the derivative. A rate of change is a derivative. But it says to find two different things. One, find the number of viewers in week 2. Well, n of x gives the number of viewers in the x week. So in this case, we're looking at x equals 2. So I'm looking for two things. The number of viewers is n of 2. And then the rate of increase is going to be n prime of 2. All right. We sort of talked about that before. We were talking about how these word problems are going to be worded to sort of signal what you're supposed to be finding. So a rate of increase, a rate of change, the change in a specific number, all of that will refer to the derivative. But if you're just being asked, find a number, use the original function. Okay, now, so I know I need to look at a couple of different things with n at week 2. If I know I'm going to be taking its derivative, we might want to rewrite this. I'm going to remind you of the algebra rule that we use to rewrite this function. We're going to be taking this as 60 plus 2x to the 2/3 power. So remember that index is the denominator of the radical, and then the exponent inside your radical is going to be the numerator. I know, I feel like I've written this exponent rule so many times, but I'm going to write it again. It is the nth root of a to the m. I think it's generally written that way, is a to the m over n. Okay. So that is the way that works from algebra. All right. So a couple things we need. Right now we can go ahead and answer the first question. We might as well, right? Find the number of viewers in week 2. Number of viewers in week 2. That's n of 2. And since you're probably going to be putting this in your calculator, you can do this either way. But I'm going to write this as 60 plus 2 times 2 to the 2/3, which is really just 60 plus 4 to the 2/3. So 64 to the 2/3. If you put this in your calculator, that's fine. You could evaluate it by hand also. You could rewrite this as the cubed root of 64 squared. And if you're like, Mrs. Faruqi, why would I ever want to do that? Well, imagine that you were taking a test and you didn't have your calculator. And you were just like, 64 to the 2/3. And I'd be like, okay, what number is that? And how would you be able to tell me anything about the viewers? If you can rewrite this and evaluate it using your algebra skills that were in your prereq, that would be very helpful to you if you didn't have your calculator. So this exponent rule, I know I've written it a couple of different ways, but it's the same as saying the nth root of a to the mth power. It works both ways. So that's why sometimes it's easier to use it this way, because I don't know what 64 squared is, but I do know the cube root of 64, and I can square it. So if you're like, wait, the square root of 64 is, yes, 8, but the cube root is 4, because 4 times 4 times 4 is 64. 4 squared is 16. Now, do you think it was 16 viewers? I don't think so. N of x gives the number of viewers of a particular television show in millions, and it's x week. Find the viewers in week 2. 16 million. So if I ask you this on a test, you must include the million. You can't just say 16. That's not technically correct. Tell me it's 16 million. All right, that's the first part of the question. The second part is talking about the rate of increase in viewership in week 2. So we're expecting this derivative to be positive because we're being told it's a rate of increase. So we need the derivative here. No big deal. Let's find n prime of x. All right, I've got n of x. To find n prime, I'm going to bring the exponent down. I'm going to rewrite the inside function. I'm going to decrease the exponent by 1. Now, I just need to find this derivative evaluated at 2. You might decide that you find this to be more helpful if you write it with a positive exponent and then use the positive 1/3 exponent. It's up to you. You can even turn that back into a cube root. Again, if you don't have your calculator, you might find that that's going to be the best thing for you to do. So it's 3 in the denominator times the cubed root of 60 plus 2x. So there are a bunch of different ways of denoting the exact same thing. All right, so now we're going to go ahead and find n prime of 2 because I'm looking for what happens in week 2. So n prime of 2 is 2 divided by 3 times the cube root of 60 plus 2 times 2, which we know is the cube root of 64. We know the cube root of 64 is 4. So I can go ahead and say, oh my gosh, you guys, I did a terrible, terrible thing. I just realized that I totally got carried away with my exponent and didn't multiply by the derivative of the inside function. I was going to say someone stop me, but no one can stop me. Okay, I forgot to use the chain rule. She's losing it. All right. I'm just kidding. I'm not really losing it. Okay. I must multiply by the derivative of the inside function. Sometimes I get so carried away with explaining one concept that it's like I forget to say something about the next concept. Hold on. All right. The 2 is the derivative of the inside function. So we're multiplying by 2 and we're multiplying by 2. So officially we have 4 over 3 times the cube root of 60 plus 2x. Sorry about that. You know, I should probably just stop the video and splice it, but it's actually very time consuming. Okay, so that means this is going to be 2 times 2, 2 times 2, 2 times 2. Sorry. Okay. But we fixed it. It's fixed. And that leaves me with 1/3. 4 divided by 4. And then the 3 stays in the denominator. Now, 1/3 million viewers per week would be the rate of increase in viewership. Now, this is actually the exact answer. If you feel like that's a really weird answer, like 1/3 million, I mean, I guess, but if you wrote it as like 0.3 million, that's really not even exact. 1/3 and 0.3 are not the same thing. So I would leave it like this: 1/3 million viewers per week. Remember, when you're putting your units on these rates of change, you don't just need a number, but you need a number per some other unit. So when we're answering the change in viewership, you need to think about the change, well, how often? And remember that we're talking about the change per week. So every week the viewership is changing. So you found 1/3 million viewers, but per week. Okay, is everything else good here? I just want to make sure I didn't forget anything else. We gotta have stuff like that happen from time to time, right? Keep you on your toes. All right, that's it. Wonderful. That was the chain rule. We're going to shift gears next time and talk about marginal functions, which is going to be a lot of application problems. Nothing too crazy, though. And then we'll talk after that about higher order derivatives. So not just taking a derivative, but taking a derivative of a derivative, which can be very exciting. And then after that, we'll focus on implicit differentiation, talking about taking derivatives of equations that may not be solved for y. Maybe they're not functions of x. And then we'll see if we have time to do some related rates and include some of that into chapter 3. And then that'll be it for chapter 3. Really, really important chapter, though. A lot of very important foundations that we're going to need all throughout chapter 4. So chapter 3 is monumentally important for the next, like basically the rest of the class. Everything depends on what you learn in chapter 3. So no pressure. Have a wonderful rest of your day. And I hope you really enjoy working on the chain rule. It's so important. So, so important.